Okay, some more definitions here. Two linear systems are equivalent if they have the exact same solution set. Two linear systems are equivalent if they have the exact same solution set. So the reason we care about this is because some systems of linear equations are much easier to tell what their solution set is than others. For example, let's take the linear system x1 minus 2x2 equals 3, x1 plus 3x2 equals 8. This linear system of equations is equivalent to x1 equals 5, x2 equals 1. The second linear system of equations is much easier to tell what the solution set is than the one up here. Oops, I didn't mean to do that. Okay. Now, these two systems are also equivalent to x1 minus 2x2 equals 3 and x1 minus x2 equals 4. So you can have many equivalent systems of linear equations. However, this middle one is really the easiest to be able to tell that it is equivalent, what its solution set is. That's what I meant to say. So a system is in row echelon form if it has two characteristics. One is that all its leading coefficients are 1. That is, if we write each of our equations with our variables in a certain order, like x1 comes first, and then the x2 term, and then the x3 term, etc., we want all the leading coefficients, meaning the first non-zero coefficient that we come to be 1. And we want each leading entry to be to the right of the leading entry in the row above it. So let me give you an example. x1 plus 2x2 plus 5x3 plus 4x4 equals 1, and x3 plus x4 equals 7. This is in row echelon form because in my first equation, my leading coefficient is 1. That is the coefficient of x1. It's just understood that that coefficient is 1. And then in my second equation, I have all non-zero terms until we get to the x3 term, and that leading coefficient is 1. Also notice that in the second row, my leading one is to the right of the leading one in the row above it. So I have sort of a stair-step effect. It goes stair-step. And the reason that we like row echelon form is it helps us determine what the solution set to a system of linear equations is. So when we are trying to solve linear systems of equations, what we want to do is try to use some techniques in order to put our system of linear equations or find an equivalent system of linear equations that is in row echelon form. So what we want to do is to produce equivalent linear systems. So the following operations always produce equivalent linear systems of equations. It's not the same linear system of equations. It produces equivalent linear systems of equations. So first, we can always multiply one equation by a non-zero constant. Okay. That means that we can take an equation and multiply both sides by the same non-zero constant. Okay, that produces an equivalent equation. Okay. Second, we can interchange two equations. That just means we can switch their order. Okay. And third, we can replace one equation by the sum of itself and a multiple of another equation. So this is the only really complicated rule that we're going to have to be careful about, but we'll do some examples of this. And as long as we only use one of these three operations, None of these changes the solution set to the system. So we will always produce an equivalent system, and in this way it will help us get to a simpler and simpler system so that we might see what the solution is. So let's go ahead and do an example. So here's our example. 2x1 plus 4x2 equals negative 2. 3x1 plus x3 equals 5, and x2 minus 2x3 equals negative 5. Now remember, there are hidden coefficients here. That coefficient in front of x2 is really a 1. This coefficient in front of the x3 is really a 1. You'll actually see me write those a lot of the time. You'll also see me really make a placeholder for the x3, so sometimes I'll write a plus 0 or a plus 0 x3, or a placeholder for this x2 like a 0 x2, and a placeholder for this x1 like a 0 x1. We usually don't write those, but that doesn't mean that they're not important. We want to make sure we save a place for them. So what we want to do is put this in row echelon form. So remember, at row echelon form, there are two requirements. The first is that there is a leading 1 in each equation. So that means going left to right. The first non-zero coefficient we come to is a 1. And then secondly, that our leading 1s go from the top left to the bottom right. Every time if I look in the row above, the leading 1 should be to the left, or if I look in the row below, the leading 1 should be to the right. So the first thing I'm going to do is just look at this first row and multiply everything by 1/2 so that I can go ahead and make it a leading 1 in that first row. Okay, so if I do that, my first row becomes 1x1 plus 2x2 equals negative 1, while the other two rows stay the same. Okay. So now I've got a leading 1 in my first row, and now my goal is to get a leading 1 in my second row. So right now I can either, to get a leading 1 in my second row, interchange the second row and the third row to make a leading 1 in the second row, or I can take row 2 and subtract 3 times row 1 from it. So I'm going to go ahead and do that second operation. I'm going to replace row 2 with row 2 minus 3 row 1. I'm not going to do anything with row 1 and row 3. I'm going to leave those the same. I'm only changing row 2 right now. So when I do that, I leave row 1 and row 3 alone. Notice that now I'm writing in the coefficient of 1s, and I'm also writing in the 0 terms. So row 1 and row 3 were left alone, and row 2 became negative 6x2 plus x3 equals 8. So now what I would like to do is, I'm trying to put this in row echelon form so that I can solve this system easier. And so I'm going to go ahead and switch row 2 and row 3 now so that I can get a leading 1 in my second row, and also so that my leading 1s go diagonally from top left to bottom right. So I'm going to switch row 2 and row 3. And I get, leave row 1 alone, and then row 2 and row 3 were just switched. Notice that the placement of x1, x2, and x3, the equal signs, the plus signs, those have not changed. So you might have seen me pause for a minute. I just write the coefficients first, and then I kind of add in the x1 and x2 and x3. That's sort of, it's not extra information. It makes this really tedious to write. So right now what I have leading 1s in row 2 and row 3, and they go in stair-step form right now. What I want now is for this coefficient of x2 in row 3 to be a 0 instead of a negative 6. And I want to do that without affecting this 0 in front of the x1. So what I'm going to do now is I'm going to replace row 3 with row 3 plus 6 row 2 in order to make this coefficient in front of x2 0 and not affect the 0 in front of x1. So let's do that. And this is the equivalent system that I get. x1 plus x2 equals -1. x2 minus 2x3 equals -5. And -11 plus x3 equals -22. So now I'm almost in row echelon form. I have one thing left to do. Can you spot it? What I need to do is make this -11 into a leading 1 instead of a leading -11. So what I'll do is I'll replace row 3 with -1/11 times row 3. Or in other words, I'm going to divide everything in row 3 by -11. And in doing so, we get a leading 1 in row 3 that is to the right of the leading 1 in row 2. So finally, I have a system in row echelon form. So here it is. And so let's think about why this is a lot easier to solve than what I previously started with. Well, this tells me x3 equals 2. And then once I know x3 equals 2, I can back substitute to figure out what x2 is. So I'm putting x3 equals 2 into this second equation, and I get x2 minus 4 equals -5, which tells me x2 equals -1. And now that I know x2 equals -1, I can take the values of x2 and x3 and input them into the first equation and get x1 minus 2 equals -1, and so x1 equals 1. So that tells me that my equivalent system is x1 equals 1, x2 equals -1, and x3 equals 2. Since we've only used operations that produce equivalent equations, this should be equivalent to our original equation. So let's go ahead and check it in our original system. X1 equals 1, x2 equals -1, and x3 equals 2 should satisfy our original system. So we had x1 is 1, x2 is -1, x3 is 2. Go ahead and verify for yourself that this is indeed a solution for our original system. What we also need to realize is that for our final solution, this system here is equivalent to this one. And since these two are equivalent, there's only one solution to the final equivalent system. That means that there's only one solution to our original system. And in that way we can say for certain that there is exactly one solution to our system of equations. Now I know all of that writing of the systems was tedious. Yes, I know it can be tedious, and we will use a shortcut, we will use technology, but for now we need to know what the process is, so we do need to be writing this out. For now that's what we're going to be doing. We will move past that in the future. So let me know if you have any questions, notice any mistakes. I am not above making arithmetic mistakes, so please ask.